First, I think you all know Fibonacci numbers. Calculate Fibonacci numbers. The form, pretty simple. Yeah. Recurrence relation, initial values, f0 equals 0, f1 equals 1. Then recursion, f sub n equals fn minus 1 plus fn minus 2 for n greater or equal to 2. Yeah. That formula is so simple, but very famous. Why so famous? Because there are so many great properties. Yeah. In this class, we will not learn those, magic properties. Those properties just like magic. So yeah, I cannot imagine how people derive all those, unbelievable properties. Yeah. Anyway, here we just learned the simplest formula in Fibonacci numbers. If we use the recurrence formula to produce first a few Fibonacci numbers, you can see sequence number like that. Yeah. All right, so the question is, when n is large, the problem size is large, how to find Fibonacci number f sub n in a fast way, in a very fast way. Okay, yeah, all right, our plan. So let us make the plan. All right, first we solve it algorithmically. We solve it using computer algorithm. Yeah, that's algorithmically, computer algorithm. Okay, yeah, that should be easy because we have the recurrence relation. Write a function, implement this recurrence relation. How easy it is. Very easy. You can say trivial, all right? You can say trivial, yeah. But a lot of things, a lot of special points behind it. Yeah, we will learn. So we will write a computer program, but there are several different ways to write. We will compare different ways to write program, implement this recurrence relation. Yeah. All right. Number two, solve it mathematically. On paper, we want to solve this recurrence relation to derive a formula for it. So we will do two things for this problem, our problem number 11. First, let us do the first part relatively easier, so let us do first. Fibo function, let us write recursive function, Fibo, initial values, then return sum of two smaller Fibonacci numbers. That simple, right? So this is our first implementation. Yeah. If it is so simple, what can we learn from there, right? This simple thing, what can we learn from it? Yeah. First, this method solves the problem correctly. The answer is correct. Yeah. No argument on that. Correctness. No argument on that. But do you know how slow it is? Is it slow or not? Yeah, that's the question. Yeah, that's the main question. Is it good implementation? Answer, it is horrible in implementation. extremely slow. Extremely slow. Horrible implementation. How can you see that? How can you see this method is very bad? Yeah. Yeah. In our project number 2, we will compare 3 different methods. 3 different methods. Project number 2, project plan. All right. Compare efficiency for 2 different. There is a third one. Yeah. Third one probably I set as optional. Third one I set as optional. Yeah. 2, so you need to compare. Yeah. Third one, a little more advanced. Yeah. So I set as optional. Yeah. All right. Compare efficiency to calculating Fibonacci numbers. Yeah. All right. How bad is the algorithm? Yeah. Can we improve it? If it is so bad, can we improve it? We need to find the problem first. If we can find the problem, where is the problem here in this implementation? If we can identify the problem issue. Yeah, the problem. That specific problem property, yeah, then we can improve it. Yeah. All right. Yeah, here I want to draw a diagram to show you, to reveal the problem place. The problem place. So, what kind of diagram? So let me show you. Draw a recursion tree. We draw a tree. Recursion. Recursion. We use a tree to represent recursion. Now you can see what is the problem. Yeah. Let's start from the root. Yeah. Here I just draw a relatively small tree. So our root, we want to calculate fiber of 6. That's a small number, easy calculation. But if we draw a tree, you can see something special. In order to find fiber of 6, you need to find a value, fiber of 5, fiber of 4. Yeah, so you have 2 branches of the tree. Yeah. When you find fiber of 5, you need to calculate fiber of 4, fiber of 3. All right? Fiber of 4, you need these 2 smaller fiber numbers, and so on. Right? If I draw the whole tree, look at that. How about this tree? Can you see something, some special property in this tree? Can anyone say some obvious property in this tree?
7. I think the values are something.
Yeah, that. Any other properties? Yeah, yeah. That's but other bigger property, big, you know. Duplicates, repeated, some numbers repeated. Yeah, notice that, right? Yeah, look at that. How many times one fiber number repeated? Right? Observation. Look at fiber 2. How many times it is repeated? Right? Yeah, here 5 times. But we only draw a small fiber tree, the same number already repeated 5 times. Think about if you draw fiber of 100, how many times repeated? Right? 100. It's scary. Is this cause the slow computation problem? Right? This would really cause slow performance, slow computing performance. Yeah. Because why we need to do redundant computation so many times? One single fiber number, we only need to do once. Why you need to do, dozens of times? Think about that. Redundant, right? Unnecessary and redundant. And you consume too much computing resource with the redundant work. How about that? Can you cut off that redundant work? If you can cut off, you save big time. You save computing resource big time. Think about that. The next question, how to remove redundancy. How to remove redundancy. Yeah, our next question. Yeah. All right, yeah. Too much redundant calculation. So our next topic, how to improve the algorithms. Method one, iterative algorithm. Yeah. The goal, eliminate redundancy. That is the goal, eliminate redundancy. All right. Method one, very simple. We use an F array, yeah, two initial values. Then we just run a for loop to do the calculation. How about that? How simple? Method one, just this simple. But if you look at this for loop, we do not do any redundant calculation. Each fiber number is only calculated once. How about that? Each number we do not calculate more than once. How about that? So this method should be much faster than the previous one. Much faster. Redundancy eliminated. All right? Yeah. All right. Method two, another one. Yeah. Another one. So method two, we still want to use the recursive algorithm. Yeah. Because recursive algorithm, we know it is very important. Very important. Sometimes we cannot convert it to iterative method. Like the Tower of Hanoi. How can you convert it to iterative method? No way. Right? So many times recursive algorithm must be used. But the question is, when you use the recursive algorithm, can you eliminate redundancy, redundant computation? Yeah. So here we have to solve this problem. You have to use the recursive algorithm, but removing redundant computation. Yeah. So that's our second problem to solve. Let us look at a solution. Solution pretty simple. Yeah. Use an array to store calculated values. That's the expense. That's the cost you pay. Yeah, because when you use array to store values, you need to pay some cost, right? But this cost, this investment you pay, high rewarding, yeah, you will get a lot back, You will get a lot of, improvement back. Make sure that no value is calculated more than once. Yeah, in our implementation, we need to make sure this property holds all the time. Yeah. All right. Now, let me write the code. Yeah. We store this function, fiber of n value in F array. Yeah. Initially, we set the array 0. Okay? Yeah. Here, we use the array called non-F array. Non-F, yeah, you know the meaning. The fiber values in non-zero values, non. So non-F. Yeah. All right. Initially, this non-array, F array, 0. All elements 0. Now, you still run the recursive function code, but when you do it, just do one special step. All right. The first, after declaration S, the first line, if the known value greater than 0, don't do the calculation, just return the value. You can see this step guarantees each Fibonacci number is only calculated once, exactly once. Because the second time, you can call this line. You already get a value. You don't need to recalculate it. You don't need to do the second Fibonacci number calculation. After that, recurrence, all right? Recurrence, okay? But you assign the sum of two adjacent Fibonacci numbers to this known value, f of I. Okay? After you have the calculation for f of I, you assign it to the known f array. Store it. Here you can see the trick is you just use some special storage array, you solve the problem. You solve the redundant calculation problem. How good it is. How about this idea? The idea is pretty simple. Just an extra storage array. You're willing to pay a little more in storage. Memory storage, there is a cost for it. But the rewarding is huge. You improve the response time. Huge. How huge? Later we will do analysis. We will see how big it is. Yeah. And this method, there is a very important topic for this method. It's called a dynamic programming method from our chapter 8. This method, using some extra storage location to keep the known values, that method is called a dynamic programming. It's a big topic. In this class, we may not have time to cover that important big topic. But here, I give you a simple introduction. Now, this example, you get idea. And why dynamic programming? Yeah. Dynamic programming, all right? Yeah. Programming. So what's the programming? Here. Okay? Programming. Dynamic programming. What is that programming? The meaning. Yeah. It's different from our coding. That programming, different from that. This programming, the meaning here is that the storage location. Storage location, people also call dictionary. We just use a dictionary to store known information. Dynamic, because when you do, the computation happens dynamically, ongoing. Yeah. So that you keep changing your dictionary, right? So it's a dynamic dictionary. It's not a fixed dictionary, okay? It's not a fixed dictionary. It's a dynamic dictionary. Yeah. Programming here, that's the, tabular things. Dictionary, table, tabular, so you arrange your known information in a table, tabular, your known information, the same as you put in a dictionary, right? That's the meaning of programming. So dynamic programming, yeah. All right, yeah. So that topic, yeah. So you will get a much faster solution, yeah. Yeah. Here, yeah. But if we compare method 1 and method 2, you will see method 1 slightly faster than method 2. Because it does not use extra storage resource. Yeah. Although it's using array, but method 2, it looks like you do a little more work than method 1. Yeah. Slightly slower, yeah. But not too much slower. Yeah. Pretty close. Yeah. Slightly slower. Yeah. All right. But why the second method still has its value? Because this is a recursive version. Recursive version. Now, we know recursive algorithm is very powerful. Many times we need to use recursive algorithm. So that's why this method 2, although a little slower than method 1, but it has its own special value. We still need that part, recursive part. We still need it. Yeah. All right. Oh, yeah. Okay, right, yeah. Next topic. Yeah, our part D, Fibonacci formula. We need to derive Fibonacci formula, and we need to solve linear recurrence relation. Yeah. The first topic, golden ratio. Yeah. So this magic number, there is some close relation between this golden ratio and Fibonacci number. Yeah, Fibonacci number related to the golden ratio. This is a golden ratio. Yeah, the first definition. Yeah, this diagram shows you the definition. Yeah, we use line segments to define golden ratio. Okay, so this long original line segment is broken into two smaller segments, one longer piece, shorter piece. But the ratio A over B equals A plus B over A. Yeah, that is the definition. Yeah, here, let me repeat that relationship. So, long segment A plus B, the whole line segment, A plus B. The longer one A, shorter one B. Yeah. A over B equals A plus B over A. If we have that condition, then we can derive the ratio of B over A, or this A over B, that number, the golden ratio. Yeah. Okay? So we can solve it here. Because we only need to solve A over B ratio, so we introduce X equals this ratio. Okay? Then X equals 1 plus 1 over X. So you get this equation. X equals 1 plus 1 over X. Yeah. Why people call golden ratio? Because there is some nice thing. Here you can see, yeah. So this, kind of curve, nice curve, and in the picture, the famous Mona Lisa, people find this special property there. Yeah. All right. Then solving this equation should be easy. Yeah, pretty easy. Yeah. Yeah. Let us solve this quadratic equation. X squared equals x plus 1. Yeah. We just apply quadratic formula. Yeah, the standard quadratic formula. Ax squared plus bx plus c equals 0. A not equal to 0, we have this formula. Yeah. Yeah. All right. Yeah. So now that simple quadratic formula, let us just plug in the numbers. A equals 1, B negative 1, C negative 1. After we plug in, we get X equals two possible numbers. 1 plus root 5 over 2, or 1 minus root 5 over 2. Two possible numbers. But our golden ratio, remember, it is a ratio of two line segments. That should be a positive number, so we drop the negative number. 1 minus root 5, that's a negative number, so we can drop the negative number. So this special number is called the golden ratio, approximately that. Golden ratio. Yeah. All right, so, yeah. After that, yeah, so this special number, yeah, we like to use a special Greek alphabet letter Phi represent golden ratio. Just like pi, remember? Pi, yeah. So that number, we use pi, yeah. Circular, that ratio thing, yeah. Circumference over what? Diameter, right? Diameter, yeah. Pi, and another e, log base, natural log base, e. Remember? Also special symbol. Here, golden ratio, that's phi, special symbol. Yeah. So next time, because when we write formula, we don't not need to write 1 plus root 5 over 2. Yeah. All the time. Just write phi. Just write phi. Yeah. Yeah. All right. Yeah. But it may not be as famous as pi. Yeah. Pi, everybody knows that. But yeah, this one, if you use phi, many people may ask you, what's the meaning of phi? Yeah. Magic formula. Now, we want to have the formula for Fibonacci numbers. But it is so, it's hard to guess. Yeah, think about in the previous problem, we make good guess. But here, think about this magic formula. How people can guess Fibonacci number f sub n can be represented as 1 over root 5 parenthesis inside it phi to the n minus negative 1 to the n over phi to the n. How can you get this formula? Using golden ratio. And we know golden ratio non-integer, but after you do some special operations, you get a Fibonacci numbers, they are integers. Yeah, yeah. How special? Yeah. All right, yeah. How to get that? Yes. Later, we will do the calculation. Actually, in your discrete math, you learn how to solve this recurrence relation. There is one section to do that. Yeah. In this class, we just repeat it. Yeah. Yeah. I saw some students, draw some nice table, arrange some numbers. Yeah. So those students probably brought back the notes they used when they took the discrete math. Yeah. So whatever way you use, yeah. Yeah, because different instructors may use different way to solve recurrence relation like that. Yeah, yeah. But the bottom line, you just find the correct answer. Yeah, yeah. So in this class, I will use 4 steps to solve this recurrence relation. Later, I will show you 4 steps, 1, 2, 3, 4, to find a solution. Yeah. All right. Yeah. So here, yeah, before we learn how to solve the recurrence relation, we like to verify this formula. Yeah? Because we have seen this formula. It's right here. We can see it. Can we verify it? We know verification is much easier than discovery. Verification, we have many powerful tools we can use for verification. But for discovery, a lot of unknown things. You need to really figure out how to find so many unknowns. Okay? Yeah. All right. But for the proof, mathematical induction. Yes. I skipped the previous mathematical induction, but here we have another mathematical induction. Yeah. So we just do it once. Yeah. We do it on Fibonacci numbers. Yeah. To save me some time. Yeah. Okay? All right. How can you connect Fibonacci numbers to the golden ratio. Yes. Yeah. We will see when we solve the linear recurrence relation, you will see we have that formula. We have this equation. We need to work on this equation. Yeah. This equation comes from this recurrence relation. And this equation will give us golden ratio thing. Golden ratio. Yeah. All right. D.2. Verify Fibonacci formula, special cases. General case, we need to use mathematical induction. Yeah. But for special cases, we need to really do the calculation. Yeah. So here, let me show you some examples working on Fibonacci numbers when n is small number, relatively small number. Okay. All right. Verify the Fibonacci numbers. Yes. Yeah. Let us do the verification. Yeah. When n is small, we have some simple verification. Yeah. We use the mathematical induction. Yeah. N0, you plug in 0, 1 minus 1, 0, so you get 0. Okay? When you plug in n equals 1, yeah. Now a little harder than the first one, yeah, because you need to do the calculation like that, right? Yeah. And the second one, you may like to change the form, yeah, because you don't like the square root appear at the denominator, yeah. So usually people convert it to that number, yeah, that number, yeah. I hope you can see that. I hope, yeah, you can see that, yeah, yeah. Actually, the trick is simple. Yeah, let me just change the color. Yeah. Oh, what's wrong? Not working. Yeah. All right, yeah, change the color. Yeah, I mean, the way to do the simplification, you multiply the conjugate. Yeah, look at the conjugate. Root 5 minus 1, that is the conjugate of the denominator. So the top and the bottom, you multiply the conjugate. Then you get this number. Okay, yeah. After you get that expression, you do addition because they have the common denominator too, so you can get the answer easily. Okay? -1 plus 1 cancel out. 2 times root 5 and 2, bottom 2, cancel out. Root 5 and the bottom root 5 cancel out. You get a 1. Okay? Yeah. So you get this 1. Yeah. Next, now, this verification a little harder. Think about how to do the verification of F2. F2, yeah. Although you can plug in, yeah, 1 plus, you plug in 1 over that. How complicated it is. Yeah. Think about how complicated. Yeah. So still okay. So if you are very patient, yes, yeah, it's okay. Yeah, the first one, 1 plus root 5 over 2, whole thing square. All right. Root 5 minus 1, yeah, because we just did a conversion. Yeah, minus 1 whole thing square. All right? Yeah. Then you expand them. Yeah, whole thing you expand them. Yeah. Then after cancellation, you get 1. How about that? Still you get 1. Yeah. Yeah. All right. But you need to do a lot of work. See? When n equals 2, you can still do the verification, but becomes harder and harder. Okay? All right. Think about f of 3. Now it's scary, right? Scary. Yeah. Because when you see f2, already pretty complicated. How can people handle f sub 3? A little scary, right? Yeah. Here, I like to show you a different way to do the calculation. We can take advantage of the golden ratio properties. We use phi. Golden ratio has some special properties. Why not we just use some special properties here? Yeah. Yeah, I like to show you some special properties. Yeah. All right? Yeah. And to show that before we go there, before we go f3, how about let me just show you using f2 here. I do not use this way, direct way. I like to use the Fibonacci golden ratio property way. How about that? Golden ratio property way. Think about it, because we have some time. Yeah. Today in my plan, I only need to complete verification for F2 and F3. Then we are done today. All right? Yeah. So for the remaining of time, so I'm just explain how to do the verification using golden ratio properties. Yeah. All right, first, I use this F2. Yeah. Okay. How do we get golden ratio? It comes from the original quadratic equation, x squared minus x minus 1 equals 0. This quadratic equation, right? Yeah. That means if you plug in phi, it is true. It is correct. You can plug in phi. Okay? Yeah. Phi squared minus phi minus 1 equal to 0, right? How about that? It must be true. Yeah. Because it comes from there, so we put it back, it must be true. All right? Yeah. Then this equation gives us two properties for golden ratio. Two properties, obvious properties. The first property, so let me write the parenthesis here. First property, phi squared equals phi plus 1. How about that? Just to move these two terms to the right-hand side. Phi squared equals phi plus 1. First property. Okay? Second property. 1 equals phi squared minus phi. How about that? 1 equals phi squared minus phi. Yeah, 1, phi squared minus phi. Yeah. These two properties could be useful when we calculate those expressions. Okay? Yeah. Let me show you. Yeah, here I do not have much space. I just use the blank space to do the calculation. Okay? All right. Look at this, 1 over phi squared. I want to simplify this expression. 1 over phi squared. 1. When you see 1 at the numerator, can we use this expression? Replace 1 by phi squared minus phi, right? Yeah. Phi squared by the second property over phi squared. Okay? Yeah. It equals 1 minus 1 over phi, right? 1 minus 1 over phi. Okay? Okay? All right. Then, what is 1 over phi? Can we use this property another time? Okay? 1 over phi equals phi squared minus phi over phi. Can we write it as phi minus 1? Phi minus 1, all right? Yeah, phi minus 1, all right? Then you put things together, okay? Yeah. 1 minus 1 over phi, 1 minus this whole thing, we get 2 minus phi, right? Yeah. Yeah. A little messy, yeah, but I hope you can see it. 2 minus phi. How about that? Okay? 2 minus phi. Yeah. All right. So then, what is phi squared? Phi squared equals, we use first property. Yeah. So phi squared equals phi plus 1. Phi plus 1 minus 2. So 2 phi minus 1. Yeah. Yeah. 2 phi minus 1. Yeah. 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 All right. 2 phi minus 1. 2 phi minus 1. All right. Yeah. Yeah. But 2 phi equals 1 plus root 5, right? 2 phi, yeah, we go back to the original number. 2 phi equals 1 plus root 5 minus 1 equals root 5. Then root 5 over root 5 equals 1. Yeah, we get the same answer, but here we just practice the property. Although we may not simplify the calculation, we just practice these properties. Yeah, a little messy. Yeah, a little messy. Yeah, yeah, yeah. But one thing, yeah, from this example, one thing I want to convey: you just use these two properties repeatedly. Okay, use these two properties repeatedly. You can do the simplification. Yeah. When you see phi squared, you can replace it by phi plus 1. When you see 1, sometimes you can replace it by phi squared minus phi. See? Yeah. Yeah. Two properties. All right. Next, let us work on our last example, F3. First, we feel degree is too high, and we don't want to calculate golden ratio cube. That's too complicated, we feel. So we want to bring down the exponent number from 3 to lower degree. And that's our goal, but we have properties. The strategy, reduce the degree to make the calculation easier. I just show you using for F2. Now we just work on F3, but let us work on phi cube. How do we make phi cube lower degree phi expression? Lower degree phi expression, phi cube. How to work on phi cube? Do you see phi square in it? Can we say phi cube contains phi square as a factor, right? As a factor, yeah, equals phi times phi square. How about that? We split in this way, split, okay? Can we replace phi squared by another expression? Yeah. Yeah. Because, yeah. Right. Yeah. So we know that, right? Yeah. So phi plus 1. All right. Yeah. Multiply out. All right. Through out. You see phi squared again, right? Replace it another time. Yeah. 2 phi plus 1. Yeah. Now the degree much lower, right? From 3 to 1. Degree lower should be easier, right? Yeah. Let us look on 1 over phi cube. 3 too high, we want to make it smaller. Okay, all right. Can we replace 1 by phi squared minus phi? Phi squared minus phi, all right? Can we do cancellation a little bit? Yeah. One common factor, 1 phi cancel out. Phi minus 1 over phi squared. Okay, all right. Next, can we replace 1 by phi squared minus phi another time? After replacement, we have 2 phi minus phi squared. Okay? Then equals 2 over phi minus 1. All right? Now we can add them up. Right? Phi cube plus 1 over phi cube, we can add them up. Okay? Yeah. Equals -1 plus 1 cancel out. 2 common factor, we factor out. Parenthesis, phi plus 1 over phi. What is that? Phi plus 1 over phi. Okay? Yeah. Because that corresponds to phi 1, right? After you multiply 1 over root 5, 1 over root 5, 1 over root 5 both sides, that's F1, F3, F1, so F3 equals 2F1. So you get answer too. Yeah. So in this way, you just manipulate symbols of golden ratio without root 5 calculation, right? Yeah. In this whole place, we do not use root 5 anymore. See? No root 5. Okay? We just manipulate symbols. We get answer. Yeah. Although a little tricky, yeah, but I hope you can use golden ratio properties, only these two properties, in different ways. And at the end, you get the formula you want to find. Yeah. All right. Yeah. So that's everything we need to do today. Yeah. We haven't completed. We have the last step. Yeah. The last step, just mathematical induction part. Yeah. Although a lot of math computation, but I may like to go through. I may like to go through to show you how to use a complete mathematical induction to solve this problem. Yeah. Oh, after that mathematical induction, we have another topic. We need to solve linear recurrence. Yeah. So we have 2 topics left for Module 3, for this Module 3. Yeah. But for homework assignment number 2, the question I will give you, just stop here, right here. Okay? Yeah. That's the coverage. Module 1, 2, 3, 3 at this place. Yeah. The remaining 2 topics are not included, homework number 2, but for midterm, those 2 topics will be in the midterm. Yeah. All right, so that's it. Yeah. Next time we will start Module 4, but before Module 4, let me complete 2 topics of Module 3. Yeah. All right, so yeah,